from ATBU Bauchi. I don't have to say much because all that I have to say is contained in this material. This research is about only polytechnics that offer electronics 3 in the whole of North Central State. So your lecturer is going to do justice to the rest of it.
On the very subject called electronics 3. Normally we have the code, it is EC 244. That's the subject code. And it will be discussing operational amplifiers. Before the advent of computers, this very topic we're discussing today was in existence. And what is an operational amplifier, normally called op-amp? There are some textbooks you see them writing op-amps. That's operational amplifiers. What are those operations that it carries out? These are the kind of things we're going to discuss. So an op-amp is a high-gain electronic voltage amplifier with 2 inputs and a single output. It is capable of performing operations as addition, subtraction, integration, and differentiation. You understand? So, primarily for those of you that are studying computer science and those of you that are studying other courses, as we're here together, you're enjoying this course as for students, you encounter from various subject areas this very topic called op-amp. And the general overview of this topic is to see how it affects the instruments that are designed and how it is able to improve your life. Okay? So, as I earlier said, an op-amp is a high-gain electronic voltage amplifier. The reason is that with any little input you put to it, it gives you a very high output. So the symbol of an op-amp is like this. These are inputs, input terminals, right? And this is the output what? Terminal. And you can see V at means output voltage. V1 and V2 means voltage into the, sorry, this should be the negative or the positive, you can invert anyone. This is the inverting terminal and this is the non-inverting terminal. What do I mean by inverting and non-inverting terminal? The inverting terminal is the negative terminal, while the non-inverting terminal is the positive terminal. Let me just write it for you to understand. This is a non-inverting what? Terminal. And this is the inverting terminal. The reasons why we're having these two terminals is because it can carry out a lot of functions. It can work as a summer, it can work as a voltage follower, it can work as a comparator. So, having seen this, you know that anytime this op-amp, anytime there's an input at this level here, if there's an input at V1, let's take for instance, let me use another marker to demonstrate to so that you. Now, if for instance we have an input like this, are you getting me? Yes, this is for V1, or have another one like this for V2. By the time this input signal enters the negative terminal of the op-amp, the output is going to be inverted. You can see the positive, negative, and this one is actually negative, positive. And if the V2 signal, which is the same in phase, in frequency, and in magnitude. I don't know having the same phase, frequency, and magnitude. That is everything is starting is the same as this other one, right? So this is positive, negative. If the signal enters the positive, which is the inverting, the non-inverting, sorry. This is the non-inverting terminal, this is the inverting, sorry. This one here, when it enters here, what happens is that the output is going to be like this. That is going to be in phase to the input, and this one will be out of phase to the input. Can you see how it behaves? So there are basic things that you need to understand even on your laptop systems, desktop systems, or even your phone that you use. Some of you may even look at it and say, oh, I'm typing something. When you type anything into a system or a computer, what happens is that it converts that write-up, your physical write-up, into machine language. And this machine language are binary numbers. Are you getting me? And when that is done, that's the time the computer will be able to understand what you are saying. It's not a physical alphabet or typing, physical numbers are writing like that. It doesn't know it that way. That's why we always try to teach you binary numbers, conversion of numbers for you to understand. So op-amps are some of these components that are used to put such assignments. Are you getting me? So with the symbol you have seen on the board here, you can see that an op-amp has two supplies. The positive supply is normally DC. Normally VCC, this is DC, this is supply. Positive and then the negative supply. You understand? So with this arrangement, you can see that I earlier said any signal that enters the negative side will turn upside down. That is out of phase. Okay? Can you see how this one is starting down? It's not the same shape with this one, it's starting down, alright? But this other one, as it enters, because it's a positive sign here, what it does is that it is in phase with the one at the input. Are we together? Yes. Okay. Now, have we gotten the concept of the operation of an op-amp? Also seeing the symbol of an op-amp. This one is mainly, we can say this is the symbol of an op-amp, right? This is the symbol of an op-amp. You can say this is figure 1 of an op-amp. This is the symbol of an op-amp. Is it clear there? Are you with me? So now, let us look at the general equivalent circuit of an op-amp. What is the general equivalent circuit of an op-amp? The equivalent circuit of an op-amp looks like this. And this is the voltage out. That's the output voltage, right? That's the output voltage. And then here, you have your V1, V2. These are the two input voltages that are coming, right? Yes. Okay. Then here, inside it here, you have a resistor connected again, which is called Z in, and this one Z out, and this one is a voltage gain, which VD, this is differential voltage. The reason why we're saying differential voltage is that the differences in the voltages, V1 and V2 here, determines the function of an op-amp. I don't know what I'm communicating. Yes. The differences between V1 and V2 determines the operation of an op-amp. Now, with this equivalent circuit you are seeing, an op-amp has an infinite input impedance. What do I mean by impedance? For those of you that studied science students, we can have the general formula for impedance as R squared equals to XL minus XC bracket square into this. Impedance and resistance are quite very similar, but the only difference is that the resistance, when you say impedance, it requires a reactive component. You know it very well. But when it comes to impedance, you can still have the symbol sign, but the ohm sign for this measure the ohms. Yes. Resistance measure the ohms. Yes. But the difference is that this one has a reactive component, which is an inductor or a capacitor. Have you seen the difference? Good. So the input impedance here is the sum of the resistance that exists at the terminal. Zero input, that is the input impedance. Finished resistance is the resistance that exists between the terminals of the op-amp, which you have already seen here as V1 and V2. Okay? Now, you can also have it that I told you an op-amp is a high gain voltage amplifier. Voltage amplifying device. High gain voltage amplifier. what is the gain? LV here is the open loop gain, V. LV is the open loop gain, while VD is the differential voltage. What do I mean by differential voltage? You can say VD equals to V1 minus V2. Is it not the difference? Huh? That's the difference now. V1 and V2 is the difference in this case. And for that reason, if I'm using this formula, it will give me the output, it will give me the output of this very op-amp. The formula is going to be V out equals to AV VD, where VD equals to V1 minus V2. Are we together? Yes. Now, when this happens, you are going to have V out equals to AV bracket V1 minus V2. That is, you are substituting this V1 minus V2 into the place of VD. And the voltage output of an amplifier is dependent on the voltage gain of the amplifier. And an op-amp has a high or an infinite input impedance and a zero output what? Impedance. Their out is zero output. The reason is that any resistance that is low, it will give room for more current or voltage to pass through. Is it not? If you have a high resistance, it will on level of limiting of the something to the output, right? Yes. So the Z out there is what? It has a zero effect, and this one is infinity. Infinity. This one is infinity. It has an infinity. That is, you can say here as Z equals to infinity, and the output Z out equals to what? 0, while Z in is what? Infinity. We're making progress. Yes, sir. Okay. Now let us try to look at for an op-amp to give any output, there must be a difference between the two inputs voltages. That is, an op-amp, if you have a 1 here, 1 volt, and another one, 1 volt here. You know that V1 and V2 is 0, right? Yes. Automatically you are going to have a 0 output. An op-amp does not work like that. There must be a little difference. There must be what? A little difference. One signal is applied to the input with the other inputs grounded, or the opposite polarity signals are applied to the inputs. Here, for the differential mode that we are discussing, you may have an op-amp like this. Then, one of them is grounded, and then this one is taking the supply. You have it V. Are you getting it?
Yes. Yes, sir.
You are biased one of the terminals. You have connected one of the terminals, and the other one is what? Connected to ground. So what is the probable effect of it? If the supply at this input is like this, mind you, it is connected at the inverting terminal. This is the inverting terminal, the one that is negative is inverting, right? The output you are going to have here is going to be an inverted signal. Are you getting the difference? That is, a signal enters at V in here, this is a signal, at the negative end, so it will turn upside down. Have you seen how it has worked? Then another one for the differential, another aspect of differential mode, here again is, you have a diagram like this. This will be grounded. That's a negative. Then the positive will now be. So what you are going to have here at this level is that this is the input signal to this. Normally positive, negative, pointing here. because it's connected to the non-inverting terminal. The output is going to be in same phase. Can you see the positive, positive, negative, negative? But here it was positive, negative, down. Are you getting me? Yes. Can you see the effect of it? So this is how it behaves. Here, this signal, this very one here is having the same phase, frequency, and what? Magnitude. For this one. Here we have different phase, same frequency, and then what? Magnitude. This is the difference that exists between the two. If the phase is the same for the non-inverting, the phase is the same for the non-inverting. But for the inverting, the phase is not the same because it has turned upside down. Okay? That is all about the single-ended in the differential mode as we're discussing. And I discussed the inverted and the non-inverted. And then in the double-ended, we have another one that is called the double-ended. Under the differential mode, we have double-ended mode. We have not come to this one. Are we together? We have not come to this. So the double-ended, it has look at it. Look at it very well. It's just as if right at the input we're having a signal that is positive, negative. Then the one here is what? Negative 1. And see, from the diagrams you see, the signals that are entering the input V1 and V2. Can you see one? The other top one is starting with positive, the other one is starting with a negative. This is how the double-ended mode behaves. This is the type of signal that enters here. Are you getting me? So the output is determined by the difference of the differential inputs. If the difference is positive, then the output is going to be what? In the positive in the phase. But if it's negative, it's going to be out of phase with the input signal. So if I say in phase, I mean the signal is the input signal is having the same phase, frequency, and direction with the output. But if I say out of phase, then the input signal is not in the same phase with the output signal. So that is that. So let's now look at the common mode. For the common mode, there is something key about the common mode. The common mode do have some issues that we need to critically look at. This V out, negative, positive, same phase. So here we may have something like this, positive, negative. And then here too we're having positive, negative. Connected to ground, is connected to ground. Anything that's connected to ground, it has a zero potential. Anything that's connected to ground, I'll finally go on to final F. Okay? In physics, we call it zero potential. We call it some people, some scholars prefer using that chassis, but the symbol for chassis is like this. This is the symbol for chassis, this is the symbol for earth. Earth, this chassis. So you see some scholars using this. But chassis, normally when you are talking about chassis, you look at the general body of the instrument connected to the earth. Like your refrigerator now. When you have the refrigerator, you have, and this one, on the body of that your radio, that your refrigerator that you have in your house that you're enjoying water every day, so that it will ground it in case of lightning effects. Okay? Yes. You ground it so that if there is any lightning effect. Some of you have seen buildings around and you see a maker being buried in the ground. Yes. For those of you that have not had such experience. And you can reduce the resistance of that surface by adding charcoal, adding salt. Yes. For you ladies, I'm not saying if you don't have salt in your house, go and pack down and begin to cook. No. So now, having explained that, let us come to what we're doing. The common mode. For the common mode is what, when I was saying, if the signal is having the same phase, having the same frequency, having the same magnitude, it enters here. What will happen here is that these two input signals, V1 and V2, V1 and V2, will cancel out. Cancel out. We cancel out. And there will what? Zero output voltage. There will be zero output voltage. There's no way you can have this type of signals entering an op amp. One of them must be the other way around. So you can see the common mode. The common mode is having the same phase, having the same frequency, having the same magnitude, entering an amplifier. Mathematically, common mode rejection ratio is giving us AOL over ACM. This one implies this is an open loop differential voltage gain. This is common mode gain. Can you see the difference? So this is the formula for the common mode rejection, and you can have it as CMRR. Common mode rejection here is where two signals of the same phase and magnitude enters an amplifier, and the operation of the amplifier cancels out, and there's no output. When you are designing and you don't take cognizance of this, you work from morning to the night to the following day. At the end of the year, you will have no single result. Anytime you are doing design on this kind of system, you need to have this in your mind. So let us look at op amp parameters. Already I've discussed one, but we're going to look at op amp parameters. Rejection ratio. CMRR. Common mode rejection ratio, which I've already discussed with you. I define it as unwanted signals with same polarity. Unwanted signals with what? Same polarity. I don't know having the same polarity. With same polarity on both lines or input of a differential amplifier. And for this reason, it cancels the effect or operation of the amplifier. For this reason, if any amplifier that you are designing and you're having common polarity at the input, I'm saying this for the second time. Yes. So the measure of an op amp's ability to reject common mode signals is expressed as common mode rejection. The higher the open loop voltage gain, the higher the common mode rejection ratio, and the lower the common mode gain. The lower the common mode gain. Just as we're talking about variation in this case, right? And in variation, we say, let's say in Ohm's law, if you say I equals to V over R, when the current is increasing, the resistance does what? Decrease. And if the current is increasing, the voltage will also increase. If the current is decreasing, the resistance will increase. And also the voltage will also do what? Decrease. So hold that relationship here. You will discover that when the common mode rejection, anytime the open loop gain is increasing, And the common mode is what? Decreasing. The better the performance of the operational amplifier, because it will be rejecting all those unwanted signals. I think you are filled up now. Okay. Now, so the second one we're going to look at is input bias current. Every op-amp has a differential amplifier at the input stage. I think I even drew the diagram of the internal block diagram of op-amp. I started with the differential amplifier input stage, voltage amplifier, voltage something gain, and then we had the push-pull stage, right? So the differential amplifier is the first stage you encounter in an op-amp. And that stage affects the input bias. What do you mean by bias? Bias is like in electronics is like trying to energizing the current supplied by the inputs of the amplifier to properly operate the input voltage. Is a DC current that is supplied by the differential amplifier to do what? Operate the input state. And this is given by this relationship. This is I bias equals to I1 or I2 or 2. It's an average of the input currents. It's not average. Why divided by 2 now? When you were supposed to you are doing your arithmetic, I think you said when you want to find the average, you calculate and count the number of those things and divide by that number. Abi? Yes. We're having I1 and I2, so divide it by 2. That is the average in this case. If we have I3, then it will be divided by what? 3, and that will give us the accurate average of what we need. Okay? So we look at the input impedance. The next one is the input impedance. The input impedance, that is Z in. We already drew a diagram and we factored in the input impedance here. Okay? There's a diagram I drew like this, and something I say Z in, right? V1 and V2, something like that. That is the input impedance. And I said the input impedance has a very high, has a very high infinity. It's at infinity, right? And to do this, you can say this is obtained by the ratio of change in the differential input voltage and change in the bias current. Or we can say is the total resistance between the inverting and the non-inverting inputs. Total resistance between the inverting and the non-inverting inputs. So we can say Z in equals to inverting input resistance plus non-inverting input what? Resistance. We can also say Z in is the change in voltage at the input and what? The current that exists at the input. Okay? Those of you electrical students, I expect them to be very, very wise and understanding this topic, because we have number 4, and number 4 of it is input offset current. Is the difference of the input bias currents. The input bias currents, input offset currents. We can input offset current, we can just say this is IOS, input offset current. And then IOS equals to I1 minus I2. Simple. With the difference that is between. Difficult? Too difficult? Yeah, okay, you're romancing with it, right? The output impedance. Output impedance is the resistance viewed at the output. Is the resistance viewed at the output. Like this one, if I should increase it, this one now, then we may have Z out. Where you have negative, positive, and then grounded, we have AV, VD. Z out here is the resistance viewed at the output of the op-amp. Okay? That is just that. There's nothing much to discuss about that one. Then we look at what is called slew rate. The next one is the slew rate. Okay, I mentioned the other one, I didn't output impedance. The slew rate. Slew rate. This slew rate is something that we really need to talk about. It is a change in output voltage in response to the step input, to a change in step input. When you will have an input voltage of this, maybe something like this, V out. You understand? This is step input voltage. So what changed when there's a step input voltage? What happens to the output voltage? The next diagram will define it in details for us to see that this is what you are going to have. This is what you are going to have. This will be I, this will be V minus V max, and this will be plus V max. Are you getting me? And then here will be the change in time. Are you getting me? So if we are like trying to talk about these variables that are required here, T2. If you want to go further, you can say this is now V max minus V, positive V max minus negative V max, and then T2 minus T1. That will be another thing. So we have covered on these parameters about op amp, and then I think we need to discuss some little things. Maybe we will continue after I ask you some questions to know your responses towards what the lecture I've delivered so far. Okay? We actually started. Okay. So having studied this topic, I want to know if I have any challenge in understanding it. If you have any problem in the course of this lecture, you are free to ask questions now so that we proceed.
So I have a question here.
Yes.
The op-amp has two input units. And so can they be used alternatively, or they must be used all together at once before it works?
Yeah. Let me answer the question. Ideally, op-amps do have the two supplies. That is the positive and the negative. Okay. In the course of connection of an op-amp practically on the circuit board, or in the course of working it practically on the board, you must have the negative and the positive. But some do have a single supply. You may have a single supply with the ground, with a negative terminal or negative side. Maybe you may have one here, giving you plus 12, or maybe 9 or 5 volts. Let's put it about 5 volts. It ranges from 5 to 15 volts. 5 volts plus VCC. And then the other terminal may be what? Grounded. And there are some that takes two supplies at a time. Positive 5 and negative 5 at a time. Okay? Web materials. Materials on the web, right? 3, by knowing the number of the op amp. In this one, somebody gave you a number. Go to the market and buy this op amp. And practically, the most common op amps we have in the market are UA741. That is a very common op amp you can see. And there's another one, something TLO something, which I've forgotten the other form, but TLO do have op amps on them. CRs, that go with voltage, cassette recorders, and the rest. Most of the electronic systems use op amps. Anytime there's need for voltage comparison, is the op amp that comes in. Just as when there's need for voltage regulation, you have regulators like LM780509 and LM317T or the rest. But when it comes to voltage operation, the op-amp is the best. Transformer is a passive electronic component. What I mean by passive is that transformers does not act as transducers. But op-amp acts as a transducer because anything that comes at the input it quickly responds to it that way. Transformers are not active because they don't amplify. They are passive components, they don't amplify signals. But active components, electronics like transistors, ICs, amplify signals. Are you getting the difference? That's the first one. Second one is that the voltage, the supply that's needed to operate an op-amp is far, far less as compared to that which is required to operate a transformer. That is number 2. 3. The op-amp is a component that is fragile. A transformer is not as fragile as the op-amp. What I mean by is that the transformer is robust. Another point is that the op-amp has a specific temperature it can operate, and a transformer can operate beyond that temperature. You have temperature that ranges up to 105 degrees maximum. 105 degrees maximum. The op-amp, some of them may have just 75 degrees centigrade. Some 80, some 85. Okay. But any component you see having up to 105 degrees centigrade are MOSFETs, like active devices like this, are MOSFET transistors that can have that 100 degrees centigrade or more. Yes. And they are very big. They are very big. In fact, bigger than my finger. Yes. Normally, we have a surface mount terminal something. But all ICs do have something of this nature. If you take any IC you take, you must see something like this. An opening here. And this is where you start to count 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Any IC you want to use, you want to work on, check on this. Get this thing. If not, you connect it wrongly. This thing I'm saying, you can go and check, you see it. So the op-amp here uses this. But for you to know the internal arrangement for you to connect an op-amp, you must consult the data manual to show you the pin arrangement. To show you what? The pin arrangement. Not that you say because 1, then you say ground. 1 may be number 3 or 4 may be the ground. So it will not work unless you know it to check it very well. Sometimes you are compelled to go on the internet to download it. You keep it and be looking at it and be doing the connection. If you don't have a data manual booklet that can show you this is the terminal, this one is the power, this is the positive supply, this is the negative, this one is the output, this is the input. You must know it too. If you don't know it, how can you design it? There's no, it will not work that way. It has transistors connected in dielectric tone arrangement. It has really some passive components from resistors for regulations. But if you want to know more, you Google the internal structure of this value. 74. If I hear the schematic internal structure of micro A 741, that's right here you see it. It will show you, you see something. You see a big diagram that is that small thing. Are we together?
Yes.
Okay. Can we progress?
Yes.
Okay. Now we quickly look at the op-amp characteristics. 1, already we have discussed the parameters and that is the characteristics. It has infinite voltage gain. The concept of virtual ground. Generally, we have. Now, I earlier told you that for a differential input to be established in every op-amp, there must be what? A difference in the inputs. And I also told you that the formula for V out, that is output voltage for op-amp, we actually discussed, and I said it is V out equals to AV VD, and that is the differential voltage, okay?
Yes, sir.
And I said here bluntly that differential voltage, and I said where VD equals to V1 minus V2. So when you have this, you have V out equals to AV bracket what? V1 minus V2, VA, VB, VA, VB equals to, equals to this. Now, if you want to get the virtual ground, definitely the output must be equals to 0. Must be equal to what? 0. And if the output is equal to 0, what are we going to derive from this very concept? VA minus VB equals to 0. Then we consider that the whole of this place, then AV equals to V naught all over 0. You understand? Any number divided by 0 tends to what? Infinity. Those of you that are offering mathematics, you know what I'm saying? Any number that is divided by 0 tends to what? Infinity. Therefore, the voltage gain of amplifier is always at what? Infinity. That's to tell you that it can amplify to any level. You know that when you look at the concept of individual ground, as I'm saying, we are not going to look at op-amp as an inverting amplifier. Op-amp as an inverting amplifier. We'll be talking about inverting and non-inverting. Now we're going to look at inverting amplifiers in details. This is a time that we're going to apply serious calculations on this board. But they are very simple, easy to come by, easy to assimilate, easy to retain. So now, let us look at this very major diagram that I have with me. Let me ask this question. An inverting amplifier, what does it do? If an amplifier is an inverting amplifier, that is the waveform of the output will not be the same as the input. But if it is non-inverting, it will be the same. Okay? So, let me draw the diagram of a non-inverting amplifier and show you how this voltage input, right? Are you getting me?
Yes, sir.
This R1, and then part of this is taken to as feedback resistor. That is RF. Are we there? Yes. And then the other terminal is what? Grounded. And it is grounded. Here is VA and this is VB, indicating the two input terminals, right? Indicating the two input terminals. And the current that is flowing from here, from R1, is what? IR1. This is IR1. And then when the current comes here, it divides to this place and goes to this place. So here, the feedback resistor current will be what? IF. And here we're going to have V out, right? Or let us put it V naught. Op-amp as an inverting amplifier. That's the title. Op-amp as an what? Inverting amplifier. So, let me put it here. Okay. So now, if you look at this diagram on the board, you know very well that the output will be what? Out of phase to the input. That one is for sure. Because of the name, it will be out of phase. Though the output will be a little bit larger because it's passing through the amplifier. Is it not? It's just as if you have your microphone now. And then somebody said, "Kai, for a microphone." Those of you that are very good church. Let me use the one I know. So they leading this thing. Normally these days, young ladies will come up, tune their voice, so that the whole congregation will be sleeping and they will sing it. Come and see. The voice, your voice that enters the microphone is not as large as what you are getting at the speakers. Is it not? Yes. That is the way the op-amp hears. So now, op-amp as an inverting amplifier. So we need to know something here. This one should be I1. According to Kirchhoff's law, that painted dot here is a node. This is a node, Abi. This one jam, this one jam, this one jam. That's a node. So Kirchhoff's law says any current, the amount of current that's entering a node is equal to the amount of current that's leaving the node. So by the concept of visual ground, VA minus VB equals to 0, where VA equals to 0 and VB equals to 0. Are you there? That's the way it behaves. Since the op-amp has an infinite impedance, has a very high input impedance, the current will not flow into the op-amp. I don't know whether you are getting my point. Any resistance that's high will limit the current to flow. Abi? Yes. So since the op-amp has a very high infinite impedance, since the op-amp has a high infinite impedance, Z I1 will tend to 0. This one here will tend to 0. Mind you, VA was already 0. And the impedance and the resistance that is connected here is also very high. Are you getting me? So it will give you I1 equals to what? 0. Whether you like it or not. That's what will happen. So now, what is going to happen is that we'll start looking at the current that is passing through the individual resistors that are here. Hence, IR1 equals to IF equals to IF. Then the feedback current passing through the feedback resistor.